Welcome. Today, we are going to look at multiple linear regression. It's one of the statistical techniques used to when somebody's doing research, and it's a very powerful technique in statistics. This technique uses more than two independent variables to predict the outcome of a single dependent variable. It is an extension of simple linear regression, which uses only one independent variable. And the goal of multiple linear regression is to model the linear relationship between the explanatory independent variable and the response dependent variable by fitting a linear equation to observed data. Now, the regression equation is a mathematical formula which expresses the outcome variable to the independent variable, and it has this format. Y equals to B 0 plus Bx 1 plus B2x I2. Then it continues depending on the number of variables you are having in the entire equation. If you are having 6 variables, then this last number will be 6. If you are having 12, then this last number P will be equal to 12. But the last number is the error. Whenever you are calculating the multiple linear regression, the independent variables you are entering in your equation, they might carry an error. And this error is expressed at the end of the equation, as you are seeing here. Now here, y1 is the dependent variable, and this is what you are trying to predict. And x, there are several of them here. This one there, this one there. They are the independent variables, the factor you think influences y. And this first one, beta 0, is the y-intercept. The value of y when all the x variables, when all the independent variables are equal to 0. So we are going to model these in this lesson. We are going to see how we come up with this kind of equation when you are doing your data analysis, when you're having several independent variables. And we are going to see how we can come up with such like an equation as we proceed in this lesson, so that at the end of the day, we'll be able to say that this variable influences, this independent variable influences the dependent variable. You might be having several variables. Let me say, we said more than 2, 3 variables, or 4 variables, and when you put them into this equation, you'll be able to see which variable, independent variable, predict the outcome variables. Let me repeat here. This y is our dependent variable. And this is the variable where you'll try to predict. You'll try to estimate the value when you have input the several independent variables. Now, we have B1, beta 1, beta 2, and B3. There might be several of them. These are the regressional coefficients, and in simple terms, you call them the slopes. They represent the change in the y for 1 unit change in that specific x, assuming all variables remain constant. Now, I talked of this last letter here. It is the error term or the residuals. And this accounts for the variation in y that cannot be accounted or cannot be explained by the dependent variable. Now, as we dig in, we will see how to formulate such an equation. And because it has several other variables, we call it a multiple linear regression. There are several assumptions which you are supposed to put in mind when you are using multiple linear regression. In order for your results to be valid, you must meet these assumptions before you are allowed to use this statistical technique. The first one is linearity. Linearity is the relationship between the independent and dependent variable, and this relation should produce a linear when you draw it on the graph, there must be a linear relationship. The multiple linear regression assumes that the change in the dependent variable, which is y, is proportional to the change in the independent variable, which is always x. And this means you can draw a straight line on the plane through the data. Now, this is what I'm saying. There are several points, like on my image here, there are several points. And when you put on this point through a line of the best fit, you can be able to draw, like the green line you are seeing, it is a straight line that we have been able to draw in this data. So we are producing a straight line in the data. And to be able to follow this straight trend, this is what we are calling a linear relationship. There are some other relationships which are not linear. For example, I have a relationship here. This relationship you see with the blue color dots. If you try to draw a line through the blue color dots, you will produce a curve. You're not producing a straight line. So this one is a non-linear relationship. So if you have such a relationship, then know that you are dealing with a non-linear relationship. Data points follow a curve, and they are not following a straight line like previously we had here. Here, when you draw this, you are producing a straight line through the data points. But in the next area here, we are not be able to produce a straight line, and this one is a non-linear relationship. So when you get such a data points, then know that we have not met this assumption, and you are not going to use multiple linear regression. Another one is the one shown on the screen. This one is not producing a straight line. It's producing some sort of an exponential relationship. And this one, you see, when you draw this one, you are not producing a straight line through the data points. So this one is an incorrect linear model, and you cannot use multiple linear regression because you will not have made the assumption of linearity. The second part of but before we go to the second part, how do you test this linearity? We create scatter plots of each independent variable against the dependent variable, and you are looking for a straight trend rather than a curve, as we have said. And when this one is violated, when this assumption is violated, your model will systematically under or over predict certain values, and you might need to transform your data, e.g. using the log x, or you might use x squared. Another assumption is the assumption of homostaticity. Homostaticity. This one sometimes is called constant variance. The variance of the error term, we talked of in the previous, when you are trying to come up with the equation. This is the error here, the last one there in the equation. This error, we are saying that it should be constant. It should be constant. And when this error is constant across all level of independent variables, if you have 3 independent variables, you have 10 independent variables, this error should be constant across all these variables. And this means that the noise or the error in your model is consistent. The spread of your residual should be the same across all the levels of your predictors. That's what we simply call homostaticity. Homostaticity is a very important thing, and when it's in your data, it affects your results, and it's not good at all. How do you test for this? You look at the residual versus weighted values plot, and you want to see a random cloud of points with no clear shape. Now, when you plot your values in this case and you produce the cone kind of a shape, then you know that this assumption is not being made. For example, I've drawn on my screen the two kinds of data points, and if you have your data, and the ideal situation of homostaticity is being shown here on the left side. This part, the ideal, the one I'm circling. Ideal homostaticity, whereby we have a cloud, we have all the points distributed. And if you have to draw a straight line among these points, like the one I've done there, it is drawn properly. But here, the data points are being divided into 2. But look at the right side where we have the problematic heteroticity in the data, where we are producing some kind of a cone shape. If your data is producing this one, this kind of a shape, a cone shape, they know that you have not met the assumption of homostaticity. You have produced heterostaticity. And this, when the data produces heterostaticity instead of homostaticity, then you have violated this assumption. I've already explained there. Now, another assumption is the assumption of independence of observations. The observations are independent to each other, and each data point should be separate, independent event. The error of one observation shouldn't tell you anything about the error of the next. So if you are having your independent observation, independent variables, These independent variables, when you are fitting them into the software that can calculate these multiple linear regression, the independent variable event, the variable, the independent variable, the error of one of the independent variables should not be affected by the other. And as such, if one independent variable can tell you about the error of the other one, it means that you don't have independent of observations. How do you test for this independent of observation? We use Tabin-Watson test, and the Tabin-Watson test is specifically designed to check for an autocorrelation, also known as serial correlation in the residuals. In a healthy regression model, the error of one observation shouldn't tell you anything about the error of the next, as we have said earlier. If they are correlated in any way, your independent assumption is broken, which can lead to artificial small standard error and a misleading high significant level. Now, the Watson values, the one we use for testing the Tabin-Watson values, or the Tabin-Watson test, has some values ranging from 0 to 4. Now, we are going to interpret these values, which usually we use when we interpreting the independent of observation. When you have positive autocorrelation, that means the values are greater than 0 and less than 2. Then, if you plot this over time, this one, it means that these values are too low, and it means that you have violated this assumption. It means that you have violated this assumption. And how do these values look like? If you plot the residual over time, they look like waves or smooth trends rather than a random noise. When you draw them in a graph, you'll see something like a wave. Then you know that this is a positive correlation, and these points, they range from points greater than 0 and points that are less than 2. Also, there is negative autocorrelation, and the values are above 2 and less than 4. Now, the rule of thumb is that when you get a value from 1.5 to 2.5, we usually say that this range is generally safe zone for many researchers. But if the points are below 1.5 and above 2.5, then you should be worried of your data. Now, what to do if independence of observation is violated? If your DW score is bad, say let me say that is like 0.5, what should you do? You shouldn't ignore it. You can do the following. 1, add the missing variable. Look at your data and add the missing variable. 2, you select the variable. This include the previous time period value as independent variable. And 3, use the generalized least squares. These are mathematical approach that accounts for a correlation between errors. Another assumption is the assumption of multi-collinearity. Multi-collinearity. You should not have any collinearity between the independent variables. The independent variables, when they are too highly correlated with each other, we say that the data has multicollinearity. How do you test for multicollinearity? We check for variance inflation factor, FI, VFI, VIF, variance inflation factor, VIF. Now, this is a numerical index that will tell you how much the variance of a regression coefficient is inflated due to its relationship with another independent variable. In simple terms, variance inflation factor measures how much a variable is doubling up on information already provided by the predictors. Now, how do you interpret this code? When you get a variance inflation factor of 1, it means that no correlation at all. The variable is orthogonal or independent to each other. And this is where the situation is ideal. And when you are doing research, this is one is rare. Then you have a value of variance inflation factor of between 1 and 5. This means that we have a moderate multicollinearity, usually considered acceptable and doesn't require action unless your model is very sensitive. Another one is a VIF of greater than 5. This means that you have a high multicollinearity. The standard error for that variable coefficient is more than double what it will be if there will be independence. You should start investigating why this is so in your data. Now, if you get a VIF of greater than 10, then it shows that you have a serious multicollinearity. The coefficients are likely unstable, meaning a small change in your data could flip a variable from significant to insignificant, or even change its sign from positive to negative. So you should be worried when you get a value greater than 10. Now, why high variance inflation factor is a problem? Now, you have been caught, and sometimes the court wants to determine the cases based on the witnesses one gives or in any trial. So you consider of these independent variables like witnesses in a trial. If you have 3 independent witnesses, then you'll assume that your case is so strong. But if you have 3 witnesses who talk to each other and that they are repeating exactly the same story, then they aren't independent. And because they are not independent, you are not getting any new information. You are just getting the same information 3 times. And as such, you are in a big mess. Now, in regression, this one will lead to unreliable p-values. And remember, we use our p-values to determine whether the variable we are testing, whether it is insignificant or significant. And also it will bring the problem of interpretation. It will be very difficult to interpret the data correctly. Now, how do you handle high variation inflation factors? If you find variable with VIF of about 15, which options you have? 1, remove one variable. If you are considering the years of experience and the age, and both of them are in the model, remove one of them. Or combine, drop this variable because you are looking at the years of experience and you have the age. They might be the one that are producing this. So remove one of them, drop it from your list, and then test again and see what happens. Second, combine them. If you cannot remove, combine them so that you can get a new variable that has an average sum of the 2, and you will see how the VIF Nice. Now, if you see the problem persists, then you increase your sample size. Sometimes a smaller sample size usually affects the results in this case. So you increase the sample size, and there you test again and you see how it's going to behave. And if it continues, you use advanced techniques, and these advanced techniques will eliminate the problem, and then you're able to get results. We have another assumption called normality of residuals. And this concept your raw data will not be normal. In our first course, we were able to consider how to use the raw data and convert it into set scores, and as a result, you draw a normal curve from the set scores. So the difference between predicted and actual value should follow that normal curve, the bell-shaped curve. This curve is very important. Why does this normality of ratios matter? This assumption is required for the p-values again and confidence intervals to be accurate. If the p-values are inaccurate and confidence intervals are also inaccurate, then we are in trouble. We are going to run into the type 1 error and type 2 error. Because when you'll be interpreting our values, we have a problem because of this. Now, how do you test for this? We use Q to Q plots, a quartile to quartile plots. If the points fall thoroughly along the diagonal straight line, then the residuals are normal. I have 2 or 4 images here of how we are testing. Now, if you plot your data points, and when you plot them, if you plot your data points and you get the figure I'm circling on the left, then this is the ideal scenario. Now, you see you can be able to draw a line through them. And this is what you're calling a normal or an ideal situation. But if you get some data, this data I'm talking of, they're able to follow the diagonal line here. That one is good. The Q plots are valid and they're checked properly. But if you get your data has this figure on the right, the first one on the above, it's a curve. You can't draw a straight line in it. You are only able to draw a curve. Or the one at the bottom here, you are also able to draw a curve like the one I've drawn. Then you know that your data has a problem. The problematic scenarios of the normal residuals are present in this data. So you don't use such a data. Also, we use the curve, the normal curve or the histogram to look at the normalities. The ideal scenario is what I'm presenting on this right side when you are using an histogram. You see, this line is fitting all through. You see, it's producing a very good normal curve. And also, you will see that this forms a bell-shaped. But when you look at the one at the right hand side here, this one is left skewed. It's left skewed. And it will not produce, does not have normality of residuals. So this assumption is violated. And when you consider this one at the bottom here, it has heavy tail residuals, and you cannot draw the bell shape in this data. And know that when you get such like an histogram, you have drawn such like an histogram, know that the assumption of normality is violated. Now, if you find that this one is violated, what can you be able to do? You have to look at your data and be able to rectify it and move on. Now, I want us to get a real example. An example of a researcher who goes out to the field, collects data, has a topic of study, goes out to the field, collects data, comes with the data, and then analyzes the data. Then he uses multiple linear regression to analyze, then predicts, and finally reports. So in this case, there was a researcher who had a topic, a study of school-based factors affecting student achievement. A study of school-based factors affecting student achievement. When you look at this topic, you must be able to get the independent variables and the dependent variables from this topic. So the dependent variable will be the dependent variable from this topic will be the student performance or examination results, because we are talking about achievement. So the dependent variable will be student performance, and examination results will form part of our dependent variable. And here we are talking about the school-based factors. Because we are talking about school-based factor, there are so many factors, but we can isolate a few factors which can form our independent variable. Some of the isolated factors, or the one that we can isolate, include staffing levels, the teacher on duty in that school, the teachers who are involved in the curriculum implementation in that school. The second independent variable is the experience, and this is the experience of the principal and the number of years the teachers have been in service. That will form the experience, because these are school-based factors. Another factor I will consider is instructional resources. And in this case, I'll look at there are so many instructional resources, might include the laboratories, might include so many other things in the school. But in this case, I'll look at the textbook availability. Another one is school discipline. So I'm going to use these 4 independent variables to see how we can use them in order for us to come up with a multiple linear regression, so that we see whether the staffing level, the teachers on duty in the school, or the years of experience the principal has or the teachers have, and the instructional resources, the number of textbooks available, and the school discipline can be able to predict the performance of a school. Now, the objectives I'm having, the specific objectives I'm having, I'm getting these specific objectives from the independent variables I'm having. So the first objective is to determine the influence of school staffing levels, that number of teachers on duty, on the student performance in the public examinations. The second one is to examine the relationship between administrative and teaching experience, that is the principal and teachers years of service, to the academic outcomes. The third objective will be to assess the impact of instructional resources availability, that's the number of textbooks, on student examination results. The fourth objective will be to evaluate the extent to which the school discipline predicts student success in public examinations. And finally, I have combined all the 4 objectives to get the 5th objective, which is to identify which of the 5 school characteristics or school-based factors, that is staffing experience, resource, and discipline, is the most significant predictor of performance in a school. Now, I have 4 null hypotheses coming from these objectives. And the first hypothesis, because you will be testing this hypothesis, and when we have tested them, we'll either reject them or fail to reject. It's very important that when you are testing a null hypothesis, you either reject the null hypothesis or you fail to reject the null hypothesis. So in this case, the first null hypothesis is there is no significant relationship between the number of teachers and the school performance. The second null hypothesis is that the experience of the principal and the average experience of teachers do not significantly predict school performance. The third null hypothesis is that there is no significant positive correlation between availability of textbooks and student performance. The null hypothesis number 4 is the school discipline does not have a significant impact on public examination results in a school. Then, null hypothesis number 5, we are combined school performance, that is the school characteristics 1, 2, 3, up to 5, do not significantly predict the variation in school examination performance. Then we are going to test all these. What you should realize is that our outcome variable is going to be denoted by Y, and the first independent variable is X1. The second independent variable is X2. The third independent variable is X3. The fourth independent variable is X4. And the fifth independent variable is X5. But we are going to have X1, X2, X3. This one should be 3. X3 and X4. After having that, I did collect some data on these variables. This is a data for the purposes of this class. And I'll bring this data here so that we'll be able to look at it. It's coming. I collected some data here, and this data, when you look at it, I have school 1, where the performance is 7.5, and the variable, the number of teachers in that school are 42, and the principal experience, this principal has been in that position for 12 years, and the teacher who taught that subject has 8 years, and there are 450 books available in the school, and used a Likert scale of scale 0 to 10, where 0 is very poor discipline and 10 is very good discipline. So I look at scale of 0 to 10, where the teacher will have to mark whether this discipline is good or bad. So I used a Likert scale to have. So in this school, the discipline was ranked having a scale of 8. In the second school, a teacher filled the questionnaire, and the performance in that school in the KCSE exam was 5.2. There are 28 teachers in the school. The principal has 5 years of experience. The teacher has 4 years of experience. The textbook there are 210, and the discipline was rated at 5. This was collected in 30 schools. The data was collected in 30 schools. As you can see, all this data. So I want us to use this data, enter this data in SPSS, and be able to run a multiple linear regression so that we see which independent variable predict the performance in the KCSE exams in the school. So I'll exit again, and I'll bring the SPSS so that we'll be able now to enter this data into SPSS. So this is the SPSS program. I have already entered these the school ID. I was giving each school 1, 2, 3, 4, 5. But since these numbers are just numbers, we are using them for the purposes of identifying the school. We are measuring them at the nominal scale. Then we have the KCSE performance of every school. Because we are getting the mean 7.5, 5.5, we are measuring these at the scale, at the scale, at the ratio scale. Then we're having the number of teachers in the school. We are counting them 1, 2, 3. Then we are using the ratio scale. Then principals experience, number of years. We are also using the ratio scale. Then the discipline, because we are using a Likert scale, we are using the ordinal scale. We are ordered. We are using, we are supposed to be using interval, but at this, let us use ordinal scale. Then, or after preparing the variable, because these are the variables we are preparing, the dependent variable and the independent variable you are preparing. Now, after preparing the variables you are going to input, then you come to the data view. Now, in the data view, because these are variables, as you saw, we have school 1, the KCSE performance was 7.5, and why it's showing 8, when I was preparing my variables, I did say that you give these 0 decimal points. But because we have decimal points here, we will have got to increase the decimal point at 1, so that when you are putting the variable here, you're going to get them coming to 1 decimal point. No, put in the wrong place, please. KCSE, this one. So when you have 1 decimal point, and you're able to see now your results coming down here. The first school was 7.5, 42 number of teachers on duty. and the principal has 12 years of experience. The teacher who filled the questionnaire has 8 years of experience, and there are 450 school textbooks, and the number of the discipline here in this school is rated 8 on the Likert scale of 0 to 10, and I said that 10 is very good discipline and 0 is no discipline. Now, all of them have been able to enter them for the purposes of this class, because I didn't want to enter now. I've prepared them and I've entered all of them here in the SPSS. Now, after this, we are going to analyze. We are going to use the multiple linear regression to analyze. How do we proceed? Go to analyze at the top here, and you click on the analyze. It will bring us a menu, a drop-down menu with so many other things: reports, descriptive statistics, tables, compare means, up, down there. But we are only interested in regression. So go where we can get regression. When you put your cursor on regression, you will see another drop-down menu coming on that. It has automatic linear modeling, linear, partial, and all that. I want us to go to linear. You click on linear. When you click on linear, there is this dialog box that comes. It's a very important box on our side. And on the left side, you will see all the variables being put there. All the variables, they are there. So, on this other side, we have this dialog box here. It is the dependent variable. And down here, we have a bigger box, which requires to have the independent variables. So, here in our data, KCSE performance, or the mean, was our dependent variable. So you highlight on it, highlight on that variable. Then there is this arrow here. There's this arrow here. You just click on it. And then it will transfer that variable to that box. Then you have the number of teachers on duty. It is the independent variable. And because it's independent variable, we click on it, and then we go down here. There's an arrow there, transfer it there. Also, because I don't want to look at each of these individually, I want to look at all of them at a go. Because there is when you can look at these variables individually. You'll have to go to the next. Then you bring in another variable. Like you got number of teachers, principal years of experience, and then you transfer that variable. Then you go to next again, and then you got number of teachers experience, and then you transfer the variable. Comes, and then you go to next again. You have the textbooks, and then you transfer it again, and then you go to next, and then you go to the discipline, and you, okay, Polly. You go to discipline, and then you look at it, and then you transfer it again. The most important part here, it is the statistics. When you go to the statistics here, there are statistics you're going to use. So we have the model fit. You highlight it by ticking that box. We have R-squared box. You tick there. We have descriptives. You bleed there. And also you're going to do some collinearity diagnostics to see whether your data has violated the assumptions or not. So you also do that there. So that you're able to see whether your data is violating this assumption. Also down here, we have Durbin-Watson, the test. So you also get to tick it. Then you say continue. Then come to the plots. On the plots here, we have the C breed and Z residuals. So this C breed, you bring it to the x-axis, and C residuals, you bring it to the y-axis. Then you click on the histogram and the normal probability plot. You tick those two. Then, after you're finished, click OK, and then wait. There is the data that is going to come, boxes that are going to come. These analyzed data is very important to us because that's what we use now to analyze our data. Here, the boxes that come when we are analyzing our data, they are the following. I want us to go to the boxes that come, the tables that come, the boxes. The tables that come are very important for us when you're analyzing our data. So I'm going back to my data now, the one we were having. At the beginning. So the first dialog box, or the first results we have, it is very important table. This table is called the model results table. And in these results, we have very important areas to look at. The first area is looking at the R value, and you read that the value down there. But the most important in this is the R squared. The R squared, we are going to look at that later. Here also we have the degree of freedom, the first one, and the degree of freedom for the second part. Now this means when you take this one and add to this, you get to 9. Then you add 1, you get 30. It means that we deal with a sample of 30. Remember that when you are getting the degree of freedom, sometimes we subtract 1. So this one is that we deal with a sample of 30. You can read your sample from there. Somebody getting the results, you'll just get the sample, the sample there. Then we have the most important part, the significant part. You have to read that part very careful. The significant part. Then we have the Tabin-Watson value here. We have talked about it, and you see the importance of this value down here. Now, the R correlation, that value R, indicates a positive linear relationship. That R value, it is capital R. I found students sometimes when they are doing their research and they bring their results, they using multiple linear correlation, they use lowercase r, which is not good. We are supposed to use, when you are using multiple linear regression, we use uppercase R, capital R. And this one actually indicates that there is a linear relationship of 0.998, which is a very strong positive linear relationship. So we say that there is a strong positive linear relationship between the combined predictors, that is staffing, experience, textbook, and discipline, on KCSE mean score. Then there is R squared. R squared. This one does not now show the linear relationship, but it shows the impact these independent variables have on the dependent variable. And we will say we multiply these R squared by 100. We multiply it by 100. Then we will get 99.6%. Then we say that this means that the variance in the student performance is explained by the 5 school-based factors. That is only 0.4% that is due to by other factors outside this model. So you multiply the squared by 100, and then you'll get the percentage of variance which the independent variables explain how they affect the dependent variables. Then the second table, but before we go to the second table, let's look at the Watson value, 1.885. This one, we said that if you get 1.5 to 2.5, then that value, it means that your assumption for independence or independence of assumption is not violated. For we have 1.885, and as we discussed earlier, the value near 0.2 suggests that the ratios are independent, and the value of 1.8 is well within the acceptable range of 1.5 to 2.5, meaning that the data does not suffer from autocorrelation, and we have not violated this rule of independence of assumption or autocorrelation. Also, there is the significant, this part, the significant, which is 0.000. This value is less than 0.05. It means that the model we are using is statistically significant. That's a very important point to note, that the value is less than 0.05. Then we are able to say that this model is statistically significant, so we can use it to interpret our results. Then the other table we have, it is called the ANOVA table. This ANOVA table will be generated, and this is how the ANOVA table looks like. It's on your screen. It has important points, very important. And I am going to look at the F and the significance. Those are very important areas which we use from this table. This ANOVA table provides a statistical test of the overall model fit, and it determines whether the independent variables, these are the predictors, as a group significantly predict the dependent variable, which is the KCSE mean score or the school performance. So in this table, let us look at the F statistics and the significance. The F statistic it is very high, indicating that the variation explained by the regression model is far greater than the variation that is left unexplained. So when you get a very high value, it means that the variation explained by the regression model is far greater than that one that is not explained. And also you are supposed to see our value, our significant value is 0.000, which is less than 0.05. Then we said that these results are highly statistical, significant. These results are highly statistical significant. And because they are highly statistical significant, we will be going back to our null thesis to see how they run out. Now here, we move on, and we have the last table. This is a very important table. It's called the coefficients table. This is the detailed part of your multiple linear regression output. And it allows you to see the individual contribution of each school-based factor. Remember that we said the number of teachers is represented by X1. Principal is X2. Experience is X2. Teacher's experience is X3. And the textbook is X4. And the discipline is X5. This is what we are going to use now to come up with our regression model, like what I'm having here. So in the regression model, I have my constant and I have the coefficients. The coefficients, beta 1, beta 2, beta 3, beta 4, and beta 5. So this beta 1, as I said earlier, this beta 1 here will go to this coefficient up here. Beta 2 is this coefficient of principal experience. Beta 3 will be the teacher's experience. Beta 4 will be the textbooks coefficients, and the beta 5 will be the discipline in the school. So when I start putting this, and there is the constant beta 0, the constant 1.025, it will be the constant there. So when I start now putting this one in this, then I will say the performance equals to, the performance is actually, we say this y, equals to 1.025, which is a constant, plus 0.069, which is the staffing level, plus 0.035 times principal's experience, minus, remember now this one is a minus. So we don't put a plus, because this value where we have teacher's experience a minus. So we put here a minus, teacher's experience, plus 0.02 times textbooks, plus 0.41 times discipline. Now, this is now going to be our multiple linear regression model expression. This is now what we are going to use as our model. And this is what it means. That the number of teachers, you look now at the significance. You go in the table, you look at the significance, and this one I've toggled this table. I've toggled this table, and you see the significance from our last table. You see teacher's experience here. It has this significance here, 0.08. and the principals is 0.314, and teachers experience at teacher staffing level is 0.08, and teachers experience here it is 0.041, and the textbook is 0.1, and the discipline is 0.0. But in this, what I'm using here, I have toggled the table so that you can be able to see these two. 0.09, 0.069, which is the unstandardized coefficient which we used, has a significant level of 0.06 here. And discipline, which has a p-value, it means that, let us go to the teachers, number of teachers. It means that this is a significant, as statistically, not just significant, is a statistically significant positive predictor. Number of teachers, because it's 0.008, it is a statistically significant positive predictor. And for every additional teacher, the mean score is expected to increase by 0.09 points, assuming that all other factors remain constant. Also, on the discipline, which is also statistically significant, for every unit increase in the discipline rating, the mean score increases by 0.410. Now, when you look at the teacher experience, the p-value is 0.41. It is a significant negative relationship. And this suggests that the teacher experience increases, score decreases, which is counterintuitive results and is likely a cost effect. There is multicollinearity that is bringing this effect. So, as a researcher, you check to see, because we know teachers with high experience produce good results. But here, it is opposite. So here you have to check for that multicollinearity in the results. And also you look at the principal experience, which is at 0.35. When you multiply it by 100, it is greater than 5%. This one will be greater than that 5%. And the other one is 1, which is also greater than 1%. These two, principal experience and textbooks, they are statistically insignificant. In other words, we say they are not significant. And because of that, the p-value is greater than 0.5. This means that we cannot confidently say they influence the performance in the school. And as a result, when we interpreting the prediction of these two, because their value is less than 0.05, they don't predict the results in the school. So when we are looking at these three, p-value of 0.08, p-value of 0.00, discipline, p-value of teachers experience P of 0.041, then when we end up interpreting them, we'll do something on the null hypothesis. Null hypothesis. In the first one, we reject the null hypothesis, the number of teachers. We reject that null hypothesis, which are saying there is no statistically significant relationship. We reject that null hypothesis. And the second one, discipline, also reject the null hypothesis. And when you reject now, we have to accept the alternative hypothesis. And the alternative one is saying, this one will say there is no significant relationship between teachers' experience and teachers, number of teachers in the school with the performance. Then this one will say that there is that relationship between teachers on duty and the results. And also on discipline, if we reject the null hypothesis, Remember the null hypothesis we are having? Let's go back and see our null hypothesis. There is no significant relation between the number of teachers and school examination performance. Say, when we reject this one here, then it means we will say there is a relationship between the number of teachers and school performance, the teachers on duty. Also, we have said we are going to reject, we are going to accept this because it is more than 0.05 for the principal's experience. For the principal experience only, because we have to divide this one to produce two hypotheses. So we are going to accept this because it's more than that. Then the books, we are also going to accept this, that there is no significant positive correlation between availability of books and student performance. But you know, in reality, because of the multicollinearity in this, it has given us these results. So you must go back to the results and check for that multicollinearity so that you can check. If it still tells you, then you have to go in the field as a researcher and see what is this that's bringing these results in this form. Then after you have finished that, then we have come up with our model. It's there. We have looked at the results and see how they are. We look at the most significant predictors, and we will say here, we look at those that are significant, and we say the teachers, number of teachers, they are significant, and the teachers' experience is significant, and the discipline. So we look at the standardized coefficient, the beta one, the beta, this one written beta here. We look at the standard and look at the highest in this. And in this case, we have 0.476. And we say, the number of teachers having the beta equals to 0.476 has the highest value of prediction. Because higher the value of prediction, then it is the one that predicts most the results in the school. And then we have discipline with the beta value of 0.373 is the second most influential. Then in conclusion, we say the number of teachers that staffing level is the most significant predictor of academic success in this model. Thank you very much. I would stop here. I will stop here for today because you have looked at this. And please, if you have any query, you can reach me so that I can be able to explain in detail where you might be having that problem. Thank you very much for listening to me today and for having this class together today. Thank you very much.